But what if you started from C? You would have no choice. So that's but then you could also build a tree twice.
Yeah.
Twice or however many samples it is. Between 0.
Yeah.
He's already blessed with you know, I have to do something for 5 minutes. It might as well be something that
Yeah.
That's what I think if you already have a starting point, that'd make it easy to contribute. Well, not easy.
Yeah.
But you know what I mean.
Yeah.
We wouldn't be thinking and building something.
Yeah.
Alright, let's start. We're going to try something new here. I'm told this room has a microphone. And in theory it's on. So I'm not entirely sure if it works. I know that you can get some feedback occasionally. We'll see how it works. Before we start, as always, a couple of announcements. Homework and project. There's a homework due on Tuesday. Once again, if you haven't started yet, now would be a good time. Not now, but after class. It's due at midnight. You have to upload files on Canvas. I think one of the TAs posted a message on the discussion board. You need to upload a PDF and a zip file with your code and the data in it. There's a template zip file that's on Canvas that you can take a look at. We will not take any binaries. If you have any binaries, that is basically you lose all points for the experiment section of the homework. We need to see your code. Are there any questions about the homework? Yes.
Could you describe how the probabilities for the Gini are derived? Because it just says the sum of the probabilities. Is it the probabilities?
It's the same way the probabilities are derived for the entropy. So entropy is dependent on the probabilities, right? So you use the same probabilities.
Okay.
It's exactly the same. Without going too much into detail, so your information gain is defined as some function of entropy.
Mm-hmm.
In fact, let's just write what it is. It's entropy of the data or entropy of the labels minus average entropy. Right? Now, who said entropy is the right thing to use? You could use Gini right there. Now, entropy itself is a function of the probabilities.
Mm-hmm.
So, entropy is a function that takes some probabilities and produces a number. Gini is another function that takes probabilities and produces a number. Just replace it.
Okay.
Does that, without giving away the answer, does that make sense?
I was just looking for more description of the Gini method itself. Is there a place we can go read on it, or? Just really sparse in the description in the
So
homework.
the Gini coefficient is another measure of impurity, just like entropy. You can define impurity of the data in different ways. In some sense, one of the more natural ways of doing it is entropy, but it's not the only one. I can ask, what is the disorder in the data? So Gini is defined as, I'm just going to use G. G is 1 minus the IPJ. Help me out.
Just
Yeah, square, right?
Yeah.
There's like two slightly different definitions. They are equivalent. Yes.
So it is different though from information gain, because information gain takes the base entropy, subtract.
Okay, so
one is one in this case, it's always one.
No. So entropy is defined as.
Brian, sorry, the information is
You have these two functions, G and H. information gain could be defined in terms of, in the class it's defined in terms of the entropy, right? You derive a different version of an information gain, let's call that Ig prime, is the Gini coefficient of the data minus of the splits. So it will look something like the sum over all values the ratio of that, let's call that SV divided by S times the Gini of SV, and this is right. So the question is not what, you don't use the Gini coefficient directly. You use the Gini coefficient to redefine the information gain, and then use the information gain that you have, the revised information gain. Does that is this thing?
So we're replacing the entropy function itself with
Yes.
the Gini function.
Exactly. Because you should ask yourself, what is the point of using the entropy function? The entropy function is just a way of asking how much uncertainty is there in the labels at this point. Gini is another way of asking, of quantifying the same thing, quantifying the same idea. Does that answer your question also?
Yeah.
Yes.
Applying this formula gives a negative value, so getting a negative value is alright.
Should you get a negative value? I haven't worked out this.
You should think Gini can't go negative.
I don't think Gini can go negative. But the difference.
This was mentioned even in Canvas actually.
Oh, I'll take a look. I don't think it should.
Gini gives a positive answer, but
No, Gini cannot go negative. The
yeah,
difference.
That's a positive thing, but when we subtract and find information gain, that becomes negative.
That's kind of weird. Are you sure?
Yeah.
Okay, I'll take a look and respond on Canvas. I'm vaguely surprised. Do you guys have anything to say? Someone in the back? No? Okay. Other questions about the homework? Anything about programming? That easy? That done? Getting good grades? I guess. If not, has anyone started? Started.
Haven't gotten very far.
Okay. Just so you know, we have office hours through the week, and please take advantage of them. My TAs love having people in their office hours. They've been complaining to me that people don't show up. So please take advantage. Once again, I noticed there's like awesome discussion on Canvas. Keep it up. I really think it's awesome that, and there was also some real live discussion board in the class just before you guys, some of you came in about MATLAB. Also okay. Another announcement about projects. You have a choice, and I described it last week. Let me just, some questions, just remind you. You have a choice. Either you decide to compete with each other, with the subset of the people who choose to compete by joining the challenge, or you pick a project of your own. If you decide to compete with the class, I choose the problem, or TAs and I choose the problem, and we'll provide the data set and we'll try to make it interesting. Not saying the competition itself will be uninteresting, but we'll try to make the data set also something entertaining, or at least relevant to some of you. Or you can do a regular project, and a question comes up, what does it mean to do a regular project? It could be one of a bunch of things. When I last thought about it, I could think of 5 different kinds of projects. It could be an application of machine learning to some problem that you care about. It could be an application of a research paper, a machine learning research paper. You could have read a paper and you're like, this is so cool and I need to replicate it. And when you replicate it, you need to be careful that you are rigorous scientifically. It could be a theory project, and as I said last week or in the last class, these are some of the harder projects to do. For example, you could prove something. You could prove some property of some learning algorithm or a learning protocol, or you could prove that something is impossible. It could be a new kind of a learning algorithm or a new protocol for a problem of your choice. So it could, for example, there's some problem in, let's say, games that you see that does not fit the kind of learning algorithms that we see because the feedback mechanism is different. You might want to design a new learning algorithm that's better suited to that, and hopefully as you go along in this class you'll be able to design learning algorithms. Or it could be your own research, or some of you are working, so it could be a slice of your own work, and that's also fine. If you're doing any of these things, contact me, shoot me a message, and it doesn't have to be right now. It could be at some point you have to give me a project proposal, so just contact me before the project proposal, just so that we are able to find out the scope of the project. And some of you, I've had both two cases, two kinds of cases in the past that are not optimal in terms of scope. One is where the project is wildly ambitious, and the other one is where the project is wildly unambitious. So your project should be at least more work than your homework, for example. That's like a minimum threshold. I'm not saying that's all it should be, but a project that's easier than a homework, I will not accept. Yes.
So if we have an idea for a project, but we aren't really sure if machine learning could apply to it or not, could we bring that to you?
Yeah, sure. Or you could, again, you don't have to do, if you don't feel like coming up with an idea, you can try to join the challenge and see where that goes. The upside of joining the challenge is that you don't have to come up with a project idea. The downside is that you'll be put on a public leaderboard. By public, I mean within the class, but still, everyone will see what you're doing. Which is, for me, very entertaining, but your mileage may vary. What I absolutely will not allow is the following kind of a project. I'm going to spend the entire semester collecting some data, and there's going to be like 3 days left, and I will run homework 1 on it. No, I need to see progress in machine learning as we go along. I don't want a project where you spend the semester collecting data, because this is not a data collection class. And I have been particularly insistent on this in the past, and I will be insistent on this now, because data collection, while challenging and for some people interesting, is not the point of this class. Any questions about any of these? If you have if you can't think of questions right now, shoot me an email or start a discussion on Canvas. Yes.
Will we know what the challenge is going to be before we have to decide?
Right. So we are actively trying to get that done. I'm hoping to have something by, say, Tuesday. I'm hoping to do, or at least the broad scheme of it, maybe not the details, but at least the broad scheme, because I'm talking to some faculty around here to get some data sets that they have that seem to be giving them some grief. And we could be the machine learning consultants for the department. Alright, so are there other questions about projects and such things? Yes, and yes.
I think we have the same question.
Okay.
When do you need team information?
Everything's you need to tell me, make this whole choice. Okay, team information plus either or choice has to come to me by Thursday, 15th. I think that's the date on the.
Okay.
There's no assignment in Canvas for it.
No, you just email me.
Okay.
Yeah. Please put CS 6350 or 5350 there. Or you know what? Maybe we can create an assignment on Canvas. We'll create an assignment on Canvas. That's probably, it will save my email inbox, and it will also save me problems with me losing your email. Yes.
On the project, do we need to implement our own algorithms in our own code, or can we explore using existing libraries such as Python's scikit-learn?
So this is a difficult question. So if it's a learning algorithm that you've already implemented in class, I would appreciate it if you use your own code. If it's a learning algorithm you've seen in class, if it's something that you've never seen that I've only talked about or mentioned, but we've not really actually gone into details, maybe you can implement it. You can use some library, but if you're going to use a library, I would like you to tell me about it, maybe even before you start using the library, so that we can iron it out. For example, I don't want you to be using a library for, say, support vector machines, because you'll be implementing your own. I don't want you to be using a library for the perceptron algorithm, because you'll be implementing your own. But if it's a, I don't know, a 200 layer deep convolutional, deep fried network, then probably you might end up having to use a library, but you have to convince me that this is the only thing that will work. Alright, so just a quick summary of the announcement. There's a homework due, there's a project information that you need to give me, and the deadline for this is September 15th. We'll set something up on Canvases. Alright, so let's continue where we were. We were talking about linear models, and in particular we were talking about linear classifiers, and in the last lecture I presented the idea of a linear classifier. A linear classifier is simply a function that, a classifier that takes some input feature x, which is an n-dimensional vector, and produces a label as the sign of some bias term plus the dot product of the weights and the features. That's a linear classifier. So now the learning problem here is figure out the bias term and the weights. The nice thing about linear classifiers are prevalent, they are everywhere. They are like, they should be a standard bread and butter classifier. It should be one of the first things that you try before you move on to more complicated ideas, because many functions are linear. Linear classifiers are extremely expressive class of functions. Should offer a good guess for hypothesis space. A linear classifier is useful even when, or at least that we'll develop with linear classifiers are useful even when the functions are not linear. Many functions are not linear. For example, we saw the XOR function, the parity function. I hope you guys, some of you went home and checked that I was not lying. But even then, there is this nice trick of blowing up the feature space that can make it into linear functions in a higher dimension, in a different space, which means any algorithms that we develop for linear classifiers can be applied even there. So this is roughly where we stopped in the last lecture. Are there any questions before I move ahead? I'll say something that I was told as an early grad student, and something that I tell every lecture. If I wait long enough, somebody will ask a question.
How do we know that given data is separate?
You have no idea that the given data is separate.
So we have to try
In fact, you never know what's a good hypothesis class for a data set. We just hope we pick the hypothesis class that is big enough to maybe be good, and yet small enough to learn efficiently, and we hope it works. If it doesn't, then we try a different hypothesis class. So there is a bit of an art in machine learning, and that is the choice of the hypothesis class. That's the choice of features. Learning is not a magic black box that you can just press a button, get a spam detector. So there was a question that came up last class, and I mentioned the answer, but I'm going to talk about it a bit more. Why is this bias term needed? So just to remind you of the picture, you have this in two dimensions. You have positive and negative classes. They are nicely separated, and you can draw this line that separates them. And this arrow represents the normal to the line, and typically the direction that the normal points to is counted as the positive side. Okay, so why is the bias term needed? Suppose you did. Okay, so it's called a linear classifier because the separating hyperplane, the decision boundary between the plus and the minus, is a line or a plane or a hyperplane. Now, suppose the bias term were 0. What does it mean? It means that we are only considering lines that go through the origin, right? If B is 0, then this line goes through the origin if this did not exist. If this term did not exist, then we are only considering lines that go through the origin, which means that we cannot classify data of this kind. So lines that, if you do not have a bias feature or a bias term, then we are restricting the expressiveness of our classifier. And this is something, it's an important lesson, it's something that even people who've been doing machine learning for like a decade or so occasionally forget. And then you'll see that the published results on this paper for this classifier, for some sort of linear classifier, is 88%. You're trying to replicate the paper and you only get 60. And everything is no idea why, until you realize that you forgot the bias feature or the bias term. Because you're considering only hyperplanes that go through the origin. So there is, if you only consider hyperplanes that go through the origin, maybe this is the best one and you're guaranteed to make mistakes, even though clearly the data set is separate. There is a line that separates it, except that you're not considering, that line is not in the set that you're considering. Are there questions about the need for the bias term? That said, there is a nice syntactic trick that lets you pretend that the bias term does not exist. What you do is, remember that the prediction is this term, sine of b plus w transpose x. That's exactly the same as sine of b plus sigma wi xi. Now, I'll be using the following notation frequently, so I'll just introduce it now. I'll write you can think of vectors as a big column, right? So it is your w vector is your w1 all the way to wn. Your x vector is x1 all the way through xn. Now, suppose I'm going to create a new w prime vector, that is, all these w's, or let's say, yeah, let's start with b and then w1 all the way to wn, and I'm going to replace x with x prime, starting with a 1 and then x1 all the way through xn. The dot product of these two terms is exactly the sum, right? What I have done is, I have taken this n-dimensional input and moved it up to the n plus 1 dimensional space, where one of the dimensions is a constant in the inputs, and learn a corresponding weight, and that weight functions as the bias term in the n-dimensional space. If you think about it, even though I'm talking about n-dimensional and n plus 1 dimensional spaces, this is just an algebraic trick. I've done nothing here except algebra, right? Question about so the claim is w transpose x plus b equals w prime transpose x, and so I only need to worry about lines or planes that go through the origin with this assumption that I'm going to be in a slightly higher dimensional space, in a d plus 1 or n plus 1 dimensional space. Question?
That should be explained later.
That's right. Okay, so let me just
There is a way of erasing these things without.
right. So the point of this exercise is really this, what I've written here. Sometimes I'll be showing the bias term explicitly when I want to actually mention it, but and sometimes I will not. Sometimes I'll just fold the bias term into the weights and pretend that there is a bias feature instead of a bias term. The bias feature is this constant 1 that I kept adding. Just by adding this bias feature, one of the weights serves as the bias term in the lower dimensional space. Remember that it's always there. If it's not there, you will probably, you cannot classify things as we saw in the previous picture. It is always there, but it can sometimes be invisibly folded into the weights using this trick. Okay? the reason that I'm doing this is so it just makes the algorithms easier. It allows us with lesser bookkeeping when we are writing down the algorithms, and in fact when you are implementing the algorithms as well. So you don't have to carry this bias term around separately, you just have to use a vector. By the way, what's a good way of implementing a weight vector? If you have to implement one from scratch. If you are doing it in some C or Java-like language, something that does not support vectors, what's a vector? Just an array. If you are not comfortable with the idea of n-dimensional spaces, just think of these as n-dimensional arrays. Are there questions? Okay, I'm going to assume there aren't any. And I'm not, this slide number may be suspect, but just a couple of reminders of things that I had posed to you as exercises. There was a conjunction on the slide and I asked you to represent a disjunction as a linear classifier. Try it out. The reason I'm stressing on this is it gives you a better feel for what linear classifiers do. And to understand the feature expansion trick, try to work out how feature expansion would solve the XOR problem. It's basically the answer, I can tell you the answer right now. The answer is you need to have, instead of just linear terms, you need to have polynomial terms. Your features will be all monomials of the original features. Your blown up feature space will consist of all degree 2 monomials. And the claim I'm making is by doing that, you will solve the XOR problem, but convince yourself of that. And if you have questions, please try it out and either tell me it doesn't work or tell me it works. Either way, I would like some feedback. Alright, so far I've been talking about classification. I want to kind of slightly switch gears a bit. I want to talk about regression now. Linear models are, the idea of linear models applies not just for classification but also for regression, and this also gives me a chance to either introduce or revisit, depending on whether you have seen it or not, linear regression. And in particular, we'll look at this thing called the least squares method for regression. So just to give an example that illustrates the problem. Say you have a car, or you want to build this app that predicts the mileage of a car using its weight and age. I'm not sure how you'll get the weight of a car, but let's say you have some way of doing it. And what you want is, using these two features, the weight and the age, you want a function that predicts the mileage. Now, of course, the mileage is not a Boolean. You have to produce a number, and this is a regression problem. The label space, the output space, is the set of all real numbers. Actually, it's a set of all positive numbers, but we'll not worry about that. Now, in one way of, once again, for regression, you need to make a guess as to the hypothesis space. What class of functions are you going to search over? And probably the most popular way of doing regression is linear regression. You assume that the output is a linear function of the inputs. So the mileage is some bias plus a linear combination of the two other features. Notice, by the way, now I'll call the bias W0 because we are assuming that it's part of the weights. Now, our goal when we are learning is to find the best W. I don't know what best means, but some definition of best. And once we've finished learning, so for every time you are thinking of a new learning algorithm or a new learning strategy or a setup, you have to ask yourself two questions, always. How do you learn it and how do you predict it? Prediction, again, is easy here. Given some new x1 and x2, that's age and weight, you just apply this function and you predict the mileage. So prediction is easy. Learning is slightly tricky. Learning is, somehow need to define what is the best mileage. Is the setup clear? Yes.
Is the W all the W's or W not to find the best W?
No, the W is, good point. Usually the notation that I use, which may not necessarily be visible, boldface represents vectors and not so boldface represent real numbers. So this is a vector, and each of these are numbers. So W represents, this is the vector W0, W1 and W2. And it's not a convention I invented, it's like a standard convention that you will see in many places. So boldfaces usually represent vectors. Alright, so just to formalize this problem as a learning problem, the input space consists of vectors. You have x's, these are your, what do you call it, in the example that we had, age and weight, and in general these are d-dimensional vectors. The output space is a set of all real numbers, and we assume that we are given a training set. As always, we are in supervised learning, we have a training set and we have m examples, and I assume that the first feature is always 1. I just described, we don't have to have a bias weight, we don't explicitly have to keep track of the bias, and what we want to do is we want to approximate the function, the label y, as a linear function of the inputs. And here W is the learned weight vector. What this means is that our hypothesis space is parameterized by a W. Every W corresponds to a different hypothesis. So we remember that we are doing search over hypotheses. Every hypothesis has its own W, so that equivalently search over the space of weights. So we now have a way of thinking of learning as this optimization problem, because we need to find the best W. We can think of learning as an optimization problem in this d-dimensional space. That's what we're going to do, in fact. But before the answer, are there any questions about the question? Yes?
This just acts like a transformation from x to y.
Yeah, sure. Yes, it's a linear transformation. It's not a transformation, it's a dot product. But yes, it's from a transformation from RD to R1, if you want to think about it. It's a projection from the d-dimensional space to the space of R.
Can our project be a regression problem?
Sure.
And does it have to be linear?
No.
Okay.
And in fact, if you're going to do a non-linear regression, I would be interested. I'm curious how you'll do it. Let's maybe talk about it. Yeah. Other questions? In fact, we'll also see another kind of regression which is extremely popular called logistic regression, which is used for classification. Logistic regression is a way of pretending that Booleans are also real numbers and then training a regressor for that. We'll see that somewhat in the last third of the semester. Are there other questions? Any? Alright, so just to, before talking about the learning algorithm, as an example, your inputs could be, this is a one-dimensional case. Your input is some point here and your output is this height. And you have to produce, given a new point, you have to produce. And with the hypothesis we are making is that we are going to find a line that takes the point x, in this case x1, to the space of y's. The input, so you should realize that we are making a choice here. It does not have to be linear, as you said. You could, for example, have chosen to use a function, a non-linear function space. You could have, but we are going to look at linear now because it introduces two interesting things. Linear regression is easy. It generalizes. It's in fact one of the standard things that people often try when they are doing regression, and it also gives me this opportunity to introduce this idea of learning as optimization. We'll see that in a bit. The input, just another picture, input could be two-dimensional, and at this point you're trying to find this plane, given a point that is in this, for example. And beyond this, pictures become useless, so let's just think of the prediction being done as a dot product. Alright, so everything is easy, except we need to know what's the best weight vector. If I could tell you what's a way to find the best weight vector, this chapter is closed. So how do you know which weight vector is the best one? Let's try to build up this definition using some intuitive ideas. So for an example in the training set, let's say you have xi and yi that come from the training set. The prediction is simply W transpose X, xi. We would like to predict Y for this example, but we have predicted W transpose Xi. So a natural way of asking what is the mistake is just the difference. But because you want to, the difference could be positive or negative, and you just want to penalize things that are far away from Y, you take the absolute value of the difference. So the cost of a mistake, you can think of it, and if you feel like this is an unreasonable definition of cost, do speak up. But what we are going to define as the cost of a mistake is the absolute value of the difference between the prediction and the ground truth. Absolute values are kind of annoying, so we'll actually end up replacing this with the square mistake. And it behaves similarly as the absolute value. Now, every weight vector will be associated with a loss. The loss of a weight vector is simply the sum of all the costs, the sum of all the penalties that it incurs over the training set. So I'll use the symbol J for the cost. The cost of this particular weight vector is the sum of all the costs that you incur over the entire training set. Okay? And this is a function that in some sense assigns a quality for every W. For every W it says this is how bad this W is. Yes?
So that's basically your residual.
Yes, exactly. In fact, if you've seen this before, this is the residual.
Okay.
Yes. The reason I'm calling it a loss or a cost is because it generalizes to other learning algorithms as well, where you don't get a clean closed form answer. But yes, if you've seen this before, this is the residual. The sum of the squared costs over the entire training set is the badness of a weight vector. And now, what's a good way to learn? Which weight vector did you pick? The one that is least bad, the one that minimizes this quantity. So the learning strategy that we'll employ is to find the W that has the least cost on this particular training set. So in some sense, we've set up the learning problem as an optimization problem. Given a training set, we'll construct this objective function and minimize it. Yes?
So sir, if X is like a 26-dimensional vector like we had earlier.
Sure.
So we'll have 2 power 16 number of iterations.
No. Why? It's a real valued problem here. W's are any numbers.
So we'll have even more than.
Do we? Actually, yes. If you are doing it the naive way, yes. But how do you minimize functions? Do you try and guess? Gradient descent. You can use calculus, right? So, in fact, I'll be stepping through that in a minute. But this is called the least mean squares regression. Least mean squares because you minimize the mean, or it's actually the sum, but we'll pretend that the denominator is there. Square error. So least mean square regression. It's also called OLS, ordinary least squares. You will see this mean square, least mean LMS regression all over the place. It's something that you should be very comfortable with. It should be like your first thing to try when you're doing regression. May work, may not work, but at least you should try it. And there are many strategies that exist, but the fundamental idea I want to introduce here is that you can frame, for these kinds of things, you can frame learning as optimization. Understanding optimization has become almost like a necessary thing to understand machine learning these days, because very often if you have a new hypothesis class like I mentioned, a 200-layer neural network, how on earth are you going to invent a learning algorithm for it? You just convert the learning problem into an optimization problem, give it to a standard optimization solver, and problem solved. So learning algorithms are increasingly becoming identical to optimization algorithms. Yes.
Why avoid 1 by 2?
Why 1 by 2? Because when we take derivatives, the 2 will cancel out. It doesn't matter, period.
And if it's a mean, then shouldn't it be 1 by n?
Yes, and again, m is a constant. So minimizing over w 1 divided by m of some function of w is the same, or let's say r min, is the same as r min over w f of w. Right? It's a constant. It's the same as r min half of w. I could put any constant there, and whenever you see this half in the minimization problem, you have to know, or you will know, that at some point you're going to take a derivative of this, because when you take a derivative of the 2, of the square, a 2 will show up and that will get cancelled out, and it just is less bookkeeping when you're writing the code. That's why it's there. So, yes?
So you're basically forming an LP for a problem?
This is not an LP. It's
an objective.
It's a quadratic objective. If you want to give it a name, it's a QP, quadratic program. But that said, in fact, for this particular objective, this objective is actually very special. You don't need to solve it by an optimization algorithm. There exists a closed form solution for this. I will be giving you an exercise at some point that gives you a hint as to how you can derive the closed form thing. But just to introduce the idea of optimization for learning, I'm going to pretend that there is no closed form solution to this and derive a learning algorithm by optimizing this objective. And the strategy that we can employ is gradient descent. Gradient descent is a general strategy for minimizing a function. If the function is nice, namely it is convex, you're guaranteed to get to the minimum. So if a function looks like this, like the thing here, your gradient descent simply says just slide down the slope, get to the bottom. The way it works is you start with some initial guess, W0 right here, and you look for the direction in which this function grows the fastest. In this case, if you increase W this way, it grows. If you change W this way, it decreases. There are only two choices, right? It's one dimensional. And the way you get that is by taking the gradient. Take the derivative of the function at this point, and the gradient gives you the direction in which the function grows the fastest. What you do is you go in the opposite direction. So there's a very nice physics analogy to this. If you want to get to the bottom of a valley, you look back, you find the direction in which it's steepest, and then you go in the opposite direction. Look again, which direction is it steepest, and you go in the opposite direction. You keep doing this by taking steps in the opposite direction of the steepest ascent, so you're doing the steepest descent. And if the function is well behaved, namely it is convex, then you're guaranteed to get to the bottom of this basin. That's the intuition behind gradient descent. So the idea is you pick a starting point, a random starting point, you find the gradient of the function at that point, and you take a step. We still don't know how big the step should be, but we take a step in the opposite direction of the gradient. And now you come to a new point. You find the gradient again, you take a step in the opposite direction of the gradient. And if the function is convex, I'll mention this multiple times. You saw a definition of convexity in your quiz. I won't be spending too much time on convex functions, partly because that's going to open up, that will be like at least a semester's worth of lectures. So for now, I'll just tell you that if a function is convex, gradient descent is guaranteed to find its minimum. And if you already seen it before, then I've not told you any new information. If not, I've given you enough keywords to do a Google search. So for least mean squares, the function we are trying to optimize is this thing here. And the recipe looks like this. Remember, this is gradient descent. So you initialize some weights, take a random guess because this function is convex, you're okay. And you keep iterating. At every step, at Wt, you compute the gradient of W, and that's this term here. And then you update W. You take a step in the opposite direction. So you say W is the old W minus some step size times the gradient. The gradient of a function, a vector valued function, is going to give you a vector, so you are basically moving along in the d-dimensional space. Here R is called the step size, it's also called the learning rate, and let's for now assume it's a small constant. There's an entire cottage industry of games to be played with the learning rate, and we'll see some of these tricks later. But for now, problem solved, right? Now can you implement it? If I ask you to implement gradient descent for least mean squares, you can do it, right? What's missing? Someone is whispering a question. There is this tiny, this has no complication. All you're doing is subtracting two vectors. You have the original vector and a gradient vector, and you're doing subtraction. Hopefully that should present no mysteries to you. The one part that might be a little mysterious is how do you compute the gradient? Calculus to the rescue. The gradient is just a function, is just a vector, right? At any point, the gradient is a vector of partial derivatives. So W is also a vector with the same number of elements, but that's neither here nor there. The way to compute the gradient is you need to fill up every element of this partial, the vector of partial derivatives, and that's all you need to do. So you take the let me work. Is there a question?
I'll let you do it. Sorry.
Go ahead.
Yeah. So, but you don't know the functions. How
Oh, you know the function.
Oh, that okay. I gotcha.
We don't care about an arbitrary function. We care about minimizing the cost function. We have invented this cost function that assigns badness to every weight, and we want to minimize the cost function. So we want to do gradient descent on the cost function.
Yeah, but your function depends on your samples.
Yes, we are assuming that we are given a training set. So we cannot do anything until we first get a training set, we construct this objective here, and then take derivatives.
Okay, so in order to calculate the gradient, you'd have to sample around the point of interest from your set.
No, which set? Which set are you talking about?
The data set.
No, so the data set is entirely compressed into or summarized into that objective. So we're not sampling a point in the data set yet. We will be doing that in the very short future. But at this point, the function we care about is this sum over every training example. We have m training examples. I iterates over all the training examples
Of the entire set.
of the entire training set, and we are trying to take a gradient of that sum.
Gotcha. Okay.
In order to take the gradient of the sum, it's a vector valued function. So, or rather, it's a function defined on the vector space. So you need to take a gradient with respect to every dimension separately. You take the derivative, the partial derivative of every dimension separately. So I'm going to work out how you do this. Once if I step through every bit of detail, it should seem very obvious to you. At some point, if you're not thinking, why is this guy going through so much detail, I feel like I would have succeeded. So, I don't think we are there yet. So we have a function, this j, and we want to take a derivative with respect to wj. One element of the weight vector, that will give you an element here, let's say w2. The derivative of a sum is simply the sum of the derivatives, right? Now, this is a square term. The derivative of a square is simply, so d by dx of square is simply 2 times, right? Same trick. So the derivative of something square is twice something times the derivative of the thing that was inside the square. Any mysteries so far? Okay, but this is easy. This is just the derivative of a linear term with respect to a wj, which means only the ijth term will show up. And now the 2's can cancel, and this answers your question why we have a half. And you just some cleanup gives you this expression. So the gradient, the derivative, the partial derivative of the objective function with respect to the jth element of the weight vector is this entire sum, is the negative sum over some expression. It's not any random expression. It turns out it has a neat interpretation. I'll come to that in a bit, but what we have here is just one element of this vector. Questions about this process? The reason I'm going slow through this is I know there are some of you who are uncomfortable with vector algebra or vector calculus, or not because you've not seen it, because it's been a while since you saw it. And so it's good to kind of step through this, and I personally think that if you feel uncomfortable about this, you have to kind of write it out yourself. Math cannot be learned by seeing. So work it out. It's not, there's no rocket science here, but it's not something that I could, it's something that you have to actually step through this derivative process and convince yourself that every step is correct.
Please could you verify what is xij?
Actually, I should have mentioned that. Thanks for bringing it up. Xi is the input vector, and Xij is xi1, xi2. So it's a d-dimensional vector. So Xij is the jth element of the jth element of the ith example, the jth feature in the ith example. Yes, that's what, thanks for bringing that up. Yes. Alright, so the nice thing is, this has an interesting interpretation. The gradient is the sum of the error, but this is no longer the unsigned error, this is the signed error, times the input itself. So every input, the amount of mistake, the amount that this input contributes to the update, because remember we'll be using this to update the weight. The amount that this input contributes to the update is proportional to the error made on that input. So on this particular example, xi, if the prediction is perfect, if it's equal to yi, then that example will not contribute to the update because we are making an additive update in the, after we do this. So let's go back to the algorithm. You initialize the w and you iterate from over this t multiple times. At every step you construct the gradient of the cost function, and we just saw how we did that. You evaluate the function at each training example to compute this error, and then sum up these things, and you get the jth element or the jth element of the gradient. And then this is just one element, and then you make an update. You update w to be wt plus 1. The weight at the t plus 1 time step is just r is the learning rate. It's the step size. The gradient gives you a direction to move. You don't know how far you should move. R is the step size. For now, assume that r is a small positive constant, and generally small r's work well. It's a hyperparameter. So in your decision tree, your hyperparameter was the depth or something. Here r becomes the hyperparameter that you give as input to the learning algorithm. But there are also ways of picking R's automatically, and we'll see one of them later on. And how long should you keep doing this? You keep doing this till you are happy. You keep doing this till you feel that your error is below some threshold. So after this, you'll have some step here that says, now I'm going to compute the value of this function, and if that value is small enough, then you say, okay, I'm done. R is the learning rate, and it's a small constant. And before talking about this algorithm itself, are there any questions about the mechanics of this algorithm? Can you implement it now? Yes?
I was wondering, because I thought, if I remember back to my linear algebra days, that it is possible to actually compute directly using, like, I think you take...
The pseudo-inverse of the matrix, yes.
Yeah.
There
So
is...
that isn't just the...
Yes, you are absolutely right.
Fast or something?
No, this particular algorithm is is unnecessary. There is a closed form solution. The reason I'm working through this whole process is I want to point out that you can frame learning as optimization. And this is not the only place where we'll frame learning as optimization. This is one of those few instances where we have a closed form solution. Closed form solutions are extremely rare. Most of the time you need to have an algorithmic solution. And this represents, or the idea of gradient descent is a general strategy. And in fact, we'll talk about that in a bit. Yes. Okay. This is an algorithm. It's a procedure, let's say. Anyone can come up with a procedure. Why does this work? Why does this give me the best W at the end of this process? And the answer is, this algorithm is guaranteed to converge to the minimum if R is small enough. But the reason this algorithm is guaranteed to converge to the minimum is because the function J is convex. And if you want to think of, if your convex functions are functions that are very loosely shaped like a bowl. There's only one minimum, and you will just get down to the bottom of that bowl by using gradient descent. But there's actually a problem. Not a problem, but an annoyance with this. So, in order to compute just one update to W, just take one step, you have to iterate over every training example and sum over the whole lot to find just one step. Now let's say that you're at some point when you're done learning, when you're halfway through learning or close to finishing, you have your W is almost good enough. In fact, let's say your W is so good that out of 1 million training examples, all but one examples are predicted perfectly. There's just one error. In order to make an update, it has to now iterate over every training example, convince itself that it's okay to get just one update. So is the question, okay, this is not a optimization question, it's a computational problem. You have to sum over all training examples to get one update. And one might ask, why do you do that? Why not just make, when you are actually computing these errors, why not just make the update to the weight vector immediately and just continue? So instead of waiting to compute the sum, once you see an error, immediately update the W and use the new W from now on. Does the difference make sense? Option A, you sum over every training example to get one update using the same W. So you fix a W, you compute the gradient, and then you get Wt plus 1. The other option is you have Wt, you go through the training examples, you see an error, immediately make an update and you get a Wt plus 1. You don't even bother to go to the rest of the examples, and then you continue using Wt plus 1 maybe somewhere in the middle. These are two different methods, right? Now, this second idea is called the incremental, or more popularly it's called the stochastic gradient descent. And the general recipe for stochastic gradient descent looks like this. You pick a random example from the training set, and the important part is random. Are you okay? So you pick a random example from the training set, and the random part is important for the convergence of this algorithm. You pretend that this one example is your entire training set, and you write down the cost function for that example. You derive the gradient and take a step. And you've already taken a step. And then you go back, you pick another random example, pretend that that other random example is the entire training set, and you take a step. And you keep doing this till you're happy. Is the difference clear? In the first case, you use the entire training set to compute take a step. In the second case, you just take a random example, take a step. Take another random example, and take a step. And this is called the stochastic gradient descent. The other one, just to provide the contrast, is called the batch gradient descent. You take the entire training set as a batch, and you need to make one pass over the data to get a single update. So the algorithm itself looks like this. It looks very similar, and it's important to kind of watch out for the difference. You initialize some W. In fact, let's call it W0. You initialize the W, and then you pick a training example. In fact, instead of picking a training example, what I'm going to say is you iterate over the training set. For every training example, you immediately calculate the gradient. And then that we had before, you update here I'm not writing it as vector addition, I'm just writing it as element wise. So you update every element of the weight vector as there's some error here. This might be a plus or a minus. Oh no, it's a plus, that's right. So you update every element of the weight vector in this fashion. Here, notice that I'm saying you do it for every training example. There's no randomness. There's an assumption here that you shuffle the data here, so that every pass you get random examples. This is in contrast to the previous case where this update was outside this for loop, basically, in some sense. The difference is the update inside the for loop or outside. This algorithm is, or this update rule for the weights is called the Woodrow-Hoff rule in the neural network literature, and it was invented in 1960, if my memory serves me right. And the nice thing about neural network literature is every update rule has its name, and this one's called the Woodrow-Hoff rule. It's hardly ever used these days because this problem has a closed form solution, but it's good to know the history of this. The reason I'm introducing this stochastic algorithm, sometimes they're called online algorithms, sometimes they're called incremental algorithms. The reason stochastic gradient descent, basically it's almost a de facto learning algorithm for any objective function. So suppose you want to invent a new learning algorithm, what you do is you don't invent a learning algorithm, you invent a new objective function on the training set, and which means that you define your own favorite way of writing down the cost function. You say that this is what I want to minimize. This is the cost of a misclassification, and you write down some definition of cost. And now you need to write down a learning algorithm. All you do is take the derivative of the cost function and just use stochastic gradient descent. So this is almost like a recipe for creating learning algorithms. And we'll see how you will be implementing stochastic gradient descent for learning multiple times. We'll see that for SVM, we'll see that for logistic regression. And it's a good tool to have in your toolbox. It's an increasingly important tool. It's so important that there are libraries that automatically take derivatives for you and get your cost function, get your steps and all these things. All you have to do is invent the objective functions, the cost functions, and that's it. That's how a lot of these neural network libraries function these days. And this has enabled us to move fast with trying out different network architectures, different hypothesis spaces, because all you have to do is invent a cost function, and everything else is provided for you by the compiler, almost, by actually a library. And it turns out that stochastic gradient descent for very large data set sizes can be extremely fast, much, much faster than the batch or the standard gradient descent, and that's why this is preferred. Just a brief discussion about the question that came up. The learning rate, what that number, that thing that we had, that R. In general, R must be small, it must keep decreasing as learning proceeds, and you can think of it as how big should your step be at every point. In the beginning, you want to take big steps because you are probably in a lousy space in the objective space. You're in a lousy place in the objective space, so you want to go as fast as you can towards the minimum. As you get closer and closer, your steps should be small because you're doing some fine tuning. That's the intuitive version. There's a math that also kind of backs that intuition up. So you need to pick a good step size, and there are sophisticated algorithms that can automatically do that for you sometimes. You need to start, sometimes choosing a better starting point may be useful. For convex functions, starting points are irrelevant because it's like a bowl, anywhere you start you're going to come to the bottom. But for more complicated functions you might have to choose a starting point. And as I mentioned earlier, these two algorithms are extremely simple. Most gradient or stochastic gradient descent algorithms look exactly like what I just showed you. The only thing that changes is the definition of the function and hence the definition of the gradient. But it's a fantastic tool to create learning algorithms because all you have to do is change the loss function and you get a new algorithm just by plugging it into this template. Questions about, yes?
So you said that the interesting part of this was choosing an objective function. It kind of sounds like unless you know your propagation function as well.
Yes, that's true. In fact, the hope is that your problem is convex. And for the longest time, until maybe say mid-2000s, people kind of restricted themselves only to convex functions. And a big shift in like the mindset that happened in the last say decade or so is the idea that okay, maybe life is not convex, and it's not convex but it's still a function, has a gradient, I can move in the direction of the steepest descent and I'll get to a local minimum, not a global minimum. Maybe that's good enough. And that's basically what's been happening in every neural network paper that you've seen or you may have heard of in the last maybe 6 to 8 years. Yes?
This thing is clear that it can be traced back to gradient descent for different loss functions, but why and different hypothesis spaces?
Sure. You can change by changing the hypothesis space. You can parameterize that hypothesis space as a different set using some set of parameters. Like a neural network will be a multi-layer neural network will be a different hypothesis space from a linear classifier. It explores a larger set of functions. We'll see that in a while, but the same recipe applies. We'll see that once we get to learn. There will be a lecture at some point on learning as loss minimization, which picks up on this exact idea and explores on it in more detail. So we'll see that.
This might be a dumb question, but so we're using gradient descent to find the minimum, and then what are we doing with that minimum?
You get a weight. Sorry, the minimum is, yes, that goes back to the original thing that we had. We have a weight vector at the end. And this weight vector, according to this algorithm, is the one that is best in terms of minimizing that loss. Which means learning is complete. Now you go out there, make predictions, make money, have things. So getting the best weight vector is the point of learning in this case. Yes?
Then what is the impact of achieving a local
Minimum
minimum
versus.
versus the global?
In this case, I should point out there is only one minimum, so local is global.
In case of non-convex functions?
I don't know. Sometimes it makes sense. Sometimes it hurts. Sometimes it helps. It's a bit of a mystery for me personally. I don't know. We hope that even if we get to a local minimum, it's not too bad, because we are talking once we come to really complex function spaces, And we're talking about, function spaces that are like 1,000 or 1,000,000 dimensional inputs, and we have a highly non-convex function in that space, so very spiky function in that space. Maybe it won't. And the best strategy to avoid that is to try out different starting points and hope that you end up in the decent enough basin. But really, at that point, it's a wishing game. Yes.
How to choose a better starting point?
You try many and hope it works. That's one answer. The other one is if you know something about your problem. If you know that, for example, these features should be positively correlated. I don't know what the actual correlation is, but they should have a positive weight. These features should have a negative weight, because if this feature increases, the output should go down. If you knew that,
So that's domain knowledge.
yes, it could be domain knowledge, but more often than not, it ends up being, guess and cross your fingers. Alright, so let me summarize linear regression before moving on. What we want, linear regression is a regression problem. What we want is to predict a real valued output from a feature representation. And the assumption that we make, remember, we always have to assume a hypothesis space. The hypothesis space that we assume here is that the output is a linear function of the inputs. And what I showed here is that you can frame this problem of finding the best weights as an optimization problem. And we looked at gradient and stochastic gradient descent. We'll never see gradient descent again in this class. We'll only look at stochastic gradient descent. Gradient descent is an awesome algorithm, but it's really slow for most situations that we'll encounter. Stochastic gradient descent is an awesome algorithm and is less slow. But we'll see stochastic gradient descent is something that we keep coming across multiple times, and it just so happens that I want to remind you, and this was pointed out by a few people, this particular optimization problem can be solved analytically on paper the way you might solve an optimization problem in calculus classes. Or the minimization, you just take the derivative and set to 0 and find the answer. That actually works here. And in fact, if I'm right, the next slide, this whole thing, we'll get to that in a bit. You can actually do it. There's like a ton of math, but I encourage you to parse it out and work it out. In fact, a couple of exercises. Use the gradient descent algorithm to solve that mileage problem. You had that example with 3 or 4 examples. You can try to implement gradient descent on that tiny thing and see if you get a weight vector. It's like a good warm-up sort of a thing, because I can tell you that your next homework will involve implementing maybe the perceptron algorithm, which will look a lot like this. So you can kind of get used to the idea of implementing these vector additions and things like that. And for those of you who like doing math, the second thing should be actually easy. For those of you who don't like doing math, I encourage you that you do this. The least mean squares regression problem can be solved analytically. I'll probably have to fix this slide. You have your data set, you define 2 matrices, you just put all the x's together. Every xi is just a column here. You just put all the xi's together, you get a d by m matrix. You put all the yi's together into a vector, you get an m by 1 vector. And I want you to prove to yourself that minimizing the objective that I had, that j of w is exactly the same expression here. This will force you to kind of, dust out some matrix. Actually, there's nothing much going on here. This will force you to just think of these matrices and vectors, and probably it's a useful exercise. But that's not the exercise itself. The real thing is I want you to take a derivative of this function, set it to 0, and show that you end up with this expression. The best weight vector for this problem can be calculated just as this expression here. So the point is that I walked you through this whole grief of gradient and stochastic gradient descent, and we need not have done it. But never fear, it's all, we'll use this again. Are there any questions? Yes.
What values are these y's supposed to take? Because we're talking about the inequalities. Is this the just positive label minus
No, here we are doing regression. Y's are real numbers.
Okay.
So, at least in this section, we are doing linear regression, so all the y's are just real numbers. In fact, this will be one of the few lectures devoted to regression, so I wanted to spend some time on it. But yes, this is just any number, which is why we are able to, which is why this whole thing makes sense. The cost function is meaningless if it was not a -1 + 1. Yes?
So why is it called online?
That's the next lecture. I was hoping to have started it about 25 minutes ago, but I don't want to start it now. There is a whole notion of learning, there's a whole way of thinking of learning that's called online learning. A one-sentence summary is, or three-sentence summary is, you're talking about a learning protocol that looks like this. You take an example is given to you, you make a prediction, and then the true answer is revealed to you, and then you update your weights, and then you throw away the example that you just saw. You get another example, you make a prediction, and then the true answer is revealed to you, and you change.
Yeah.
This mechanism is called online learning. Alright, so given that I have 3 minutes, I'll just use this opportunity to tell you where we are and where we are going. Let's get back to linear classifiers. It's important to keep this difference between classification and regression in mind. Regression is when you want to predict real valued outputs. Classification is when you want to predict discrete outputs. For most of this class, we'll be talking about booleans, namely +1 or -1, or spam or not spam, or maybe more than 2 categories. Coming up over the next weeks or months, we'll be spending a lot of time on linear classifiers. Starting maybe next Tuesday or maybe sometime in next week, we'll be looking at the perceptron algorithm. And the perceptron algorithm is incredibly similar to this stochastic version or the incremental version of gradient descent for least mean squares. So I encourage you to go over that and so that you're kind of ready for this. Perceptron and Winnow are two kinds of algorithms where learning is performed in an error-driven fashion. Make a prediction, and then if you've made an error, you correct yourself, and then you go on. And that's also called an online algorithm. Another class of algorithms for linear classifiers, not regressors, linear classifiers, is the support vector machine. Some of you may have seen it, some of you may have used it, all of you are going to implement it. We'll be looking at the gory details of support vector machines, and it's just another way of training a linear classifier. Some of you may have seen the naive Bayes classifier, or some of you may have heard of it, and we'll see how the naive Bayes classifier is also a linear classifier. Some of you may have seen logistic regression. It's a probabilistic classifier, just like naive Bayes, and it's also a linear classifier. So the agenda is, the next few weeks we'll be looking at this, and then we'll do a bit of a detour, we'll look at the theory of learning, and using the theory of learning, we'll derive an objective function that actually is called the support vector machine. And once we get past that, we'll go into probabilistic learning and then look at naive Bayes and logistic regression. Somewhere along the way, we'll see other things as well. But across all these cases, remember that these are all linear classifiers, namely the prediction in all cases is the same. Your inputs are vector, you take a dot product with some weights, you add a bias term, and if that thing is more than 0, greater than or equal to 0, then you predict positive. Otherwise, you predict false or negative. So all of these are linear classifiers, and each of these different methods has its own, historical lineage. It has its own way of analyzing what learning means, and it has its own pros and cons. So I think we are at the end of time, or end of time for the class now. So I don't want to be that much of a pessimist. So just a quick reminder, if you've not started your homework, this is a good time. And if there are any questions, please use the discussion board or come talk to us.
Okay, sounds good.